Hello and welcome to the video for section 6.4. We're going to define some logarithms, the definition, graph some logarithms, find some domains, just a bunch of different things from section 6.4. In this first part, we're going to define the logarithm. Now, the logarithm is the inverse of an exponential. Let's look at the definition above. First, if we have a function and it's equal to log base a of x, we can rearrange some of these parts of the logarithm into an exponential equation. Let's take first a look at log base 3 of 27. We have y, something we don't know, and we're going to try and figure out what log base 3 of 27 is equal to. We can rearrange this, according to our definition, as 3 to the y equals 27. In other words, we're asking ourselves the question, what is the exponent on our base of 3 to give us the argument of 27? You can kind of think of it like square roots, where we're asking the question backwards. And so in this case, y would have to equal 3, because 3 cubed gives us 27. Take a look at b. In this case, we could rewrite the equation y equals log base 4 of 1/16. We'll rewrite it according to our definition above. We have the base of 4 with the exponent of y, and that is equal to 1/16. We can rewrite 16 as 4 squared, so this gives me 1/4 squared. And then, using the definition of a negative exponent, we can move the 4 squared to the top and change it to a -2. That would give us y equals -2. In other words, what exponent do I need on 4 to give me 1/16? The exponent would be -2. Over here, if we take it, y equals log base 5 of the cube root of 25. Can rewrite that as 5 to the y equals the cube root of 25. Using the cube root as a rational exponent, we get 25 to the 1/3 power. Now we'll change the 25 to 5 squared, multiplying by the 1/3 that was already there. And simplifying this through, we get 5 to the y equals 5 to the 2/3. Now that we have the same base, y equals 2/3. So the exponent that I needed on 5 to give me the cube root of 25 would be 2/3. Since logarithms are inverses of exponentials, we know that the domain of one is the range of the other. Since the range of exponential functions is 0 to infinity, in other words, greater than 0, then the domain of a logarithm must be greater than 0. That's for the standard log base a of just an x. However, if we have something other than just an x, we can solve an inequality for the domain. We'll set x minus 1 greater than 0. This tells me that the only values for x that work are from 1 to infinity. If we're going to graph this, this is going to be a vertical asymptote of the equation x equals 1. For b, we'll set 2x plus 1 greater than 0, subtract the 1 from both sides, and then divide by 2. We get the domain for this example to be negative 1/2 to infinity. And our vertical asymptote is going to be x equals negative 1/2. Now we're going to graph a logarithmic function. So this function says f of x equals log base 2 of x minus 1. The first thing we need to find is the domain of the function. The domain of the function is found by setting x minus 1 greater than 0. Solving for x, we get that x has to be greater than 1, giving a vertical asymptote of x equals 1. So over here on the graph, we're going to have our vertical asymptote through x equals 1. We're only going to be graphing then any amount of the function to the right of that, since x has to be greater than 1. That tells us then what values of x we're going to use to plug into the function. Some of these values that we pick for x greater than 1 are not going to give us what we call integer ordered pairs. They're going to give us decimal ordered pairs, and for those we're going to eventually use the calculator to solve those. So some of these we're just going to leave as exact, and we're going to find the nice ones, the nice integer ordered pairs. We'll start off at 2 and continue on down the list for a bit. In this case I'm going to go up to 9. So for the first one, for x equals 2, we're going to plug in 2 for the x in log base 2 of x minus 1. That gives us log base 2 of 1, which says what exponent on 2 gives me 1, and that is 0. If I plug in 3, I get log base 2 of 3 minus 1, which is log base 2 of 2. What exponent do I need on 2 to give me the argument of 2? A 1. So 2 to the first gives me 2. Now if I plug in 4, I get 4 minus 1 on the inside, which gives me log base 2 of 3. And that will be some decimal approximation. That's not an exact logarithm in the sense of it reducing down to an integer. When we get to 5, however, 5 minus 1 gives us log base 2 of 4, and that is equal to 2. So I can say from here that log base 2 of 3, the prior one, is going to be somewhere between 1 and 2. If I continue on with this, 6 minus 1, log base 2 of 5 gives me a decimal. Again with 7, we get 7 minus 1, so log base 2 of 6, that's another decimal. 8 gives us the same situation, where we get log base 2 of 7, another decimal. When we plug in 9, however, we get 9 minus 1 on the inside, log base 2 of 8, and that equals 3. So let's plot some of these nice ordered pairs like 2, 0, 3, 1, 5, 2, and even though we don't have 9, 3 directly, it would be somewhere out here. And just like the exponential function, it runs along its asymptote. So it doesn't just stop at 2, 0. It'll run forever along the vertical asymptote. And there is the graph of the function log base 2 of x minus 1. Now we're going to solve some logarithmic equations by converting them into their equivalent exponential equations. So for the first example, log base 3 of 4x minus 7 equals 2. I can rewrite this as 3, the base, to the power 2 equals the argument, 4x minus 7. This reduces to 9 equals 4x minus 7. Adding the 7 to both sides, we get 16 equals 4x. X equals 4. But in this case, we do need to check our solutions with the domain. So we'll set 4x minus 7 greater than 0. Add the 7 to both sides and divide by 4. So x has to be greater than 7/4. And 4 is greater than 7/4, so x equals 4 is our solution. For b, we're going to rewrite this as an equivalent exponential equation by taking the base, raising it to the power of what it's equal to, so in this case 2, and that's going to equal the argument 64. To solve this equation, we're going to take the square root of both sides, and that gives me x equals plus or minus 8. But for the base of a logarithm, the base of the logarithm needs to be greater than 0. So x equals 8 is the only valid solution. Finally, we're going to take a look at our calculator. On the calculator, there are two logarithm buttons. The first one is what we call the common log. The common log is assumed to be base 10. If we are not writing a base, then we assume that the base is 10. That's why we call it the common log. 10 fingers, our number system is base 10, so base 10 is the common log. The other logarithm button we have is the natural log, LN button, and that is specifically a logarithm with a base of e. So for these two questions, these are just straight calculator questions. Typing in on your calculator, finding the log of 42, and we get a decimal. And that decimal, when round to 4 decimal places, is 1.6232. For the natural log, we'll just press the natural log button, 124.74, and we get that to be equal to about 4.8262. Now, what do these numbers represent? So if we look at A, that says that 10 to the 1.6232 should be about equal to 42. If I get the exact 10 raised to the power of 1.6232, that's actually equal to 41.9952. We did round the 1.6232, so those are about equal. And that's about equal because of rounding. And again over here, if I take e to the 4.8262, that is about equal to 124.7361. Pretty close to the 124.74 we originally had. And so that's how you can interpret what the calculator is actually giving you. And that's it for section 6.4.